So hello, today we're going to be doing example problems from chapter 30. Quick thing, my camera isn't working, which is funny because I'm still making a point to look right at it, even though I know you can't see me. Something's wrong with my computer, the camera's not working, I need to restart the computer, but my computer takes a really god-awful long time to restart when I do. So, sorry, no working camera today. You just get to hear me and watch my screen instead. But you still get to see this, so I guess if I want to say hi, I can just be like, hi from the darkness. So, let's do some problems. Chapter 30, there's a bunch of different things I can do in the exam. I could go a few different ways. What I did,
Hey, Dr. Lars, how you doing? Sorry I'm late.
it's okay. As I was just saying, my camera was not working, so no camera today. I'll fix it later on. So, I could go a few different ways with this, but most part this chapter is going to be photoelectric effect and then all the stuff we did after. And these problems are going to kind of cover a good amount of these. So jumping right into this first problem. Calculate the energy of a photon having a wavelength at 5 centimeters, 500 nanometers, and 5 nanometers. If you want to find the energy of a photon, once again, you can't see me, so what I'm doing doesn't matter. The energy of a photon is HF. And so if you know the frequency, it's very easy to get the energy. The thing is this didn't give the frequencies, it gave the wavelengths. But don't forget that for any wave, frequency times wavelength is the speed of the wave. And for any electromagnetic waves, that speed will be c. What that means is that frequency is c over lambda. And I'll just take that and plug it into my energy equation and say the energy of a wave is hf or hc over lambda. And if I want to find these energies, I'll just plug in. For A, it'll be 6.63 times 10 to the negative 34th joule seconds times 3 times 10 to the 8th meters per second. And this one was 5 centimeters, so 0.05 meters, which would be 3.98 times 10 to the negative 24 joules. For B, it'll be the same stuff, this whole big number. I'm not going to bother writing it again. Over 500 nanometers, or 500 times 10 to the negative 9 meters, which would be 3.98 times 10 to the negative 19 joules. And for C, it'll be the same stuff. Over, this was what, 5 nanometers? 5 times 10 to the negative 9 meters. And that's the general idea. It's pretty straightforward. There's not much going on here. This is probably a simpler problem than I should have on this packet. But the general idea is if you want to know the energy of any wave, it is Planck's constant times frequency. If you don't know frequency, get it. That's kind of all there is to that first problem. The second problem actually has more of a problem to it, and is about dealing with the work function of zinc. Oh, so sorry, any questions on this first problem before I continue?
Nope.
Okay. Second problem, we're going to talk about zinc. So, zinc has a work function of 4.3 electron volts. Now, work functions are always given in EV, but we've been working in joules. So I'm going to want to convert that real fast. Well, 1 EV is 1.6 times 10 to the negative 19 joules, which doing that work, I have it somewhere, there it is 6.88 times 10 to the negative 19 joules. And it says, what is the longest wavelength of light that will release an electron from the zinc surface? The longest wavelength of light, that would be the cutoff wavelength. Now, I've given this equation in class, what the equation for cutoff wavelength is. It's actually written right here in front of us. But to explain where that comes from again, is it comes from this right here, that Ke max is HF minus the work function. And the largest, the limit is going to be when Ke equals 0. So when 0 equals HF minus the work function, or HF equals the work function, that's going to be the critical frequency. So critical frequency is work function over H. And using the same logic we did last problem, we can say F equals C over lambda, which will give us C over lambda critical equals phi over H, which will rearrange to give the equation that I had boxed, I unboxed. And so the value, I doubt I'll fit it though, will be H 6.63 times 10 to the negative 34th joule seconds times C 3 times 10 to the 8th meters per second over the work function 6.88 times 10 to the negative 19 joules. And that'll give you a value of 289 nanometers. I just converted straight to nanometers. What that means is that is the longest wavelength of light to release an electron from zinc. Anything with a short, what is the longest? Anything with a longer wavelength, which would be anything in the visible range, won't emit any electrons because of the work function of zinc. If you want to emit stuff, it's going to have to be beneath that wavelength. In B, it says a 1.13 times 10 to the 15th Hertz photon strikes the surface. An electron is emitted. What is the maximum possible speed of the electron? Well, maximum possible speed we don't know off the top right away, but we have an equation for the maximum possible kinetic energy. And so I'll say Ke max is HF minus the work function, or 6.63 times 10 to the negative 34th joule seconds, times F, 1.13 times 10 to the 15th hertz, minus the work function, 6.88 times 10 negative 19 joules. And I can just do that math. Multiply the two numbers, subtract. I will get a value of 6.119 times 10 to the negative 20 joules. And therefore, that is my max kinetic energy. And if I wanted max kinetic energy, I'd be good. But that's not what I asked for. Now, thing is, we know how to get kinetic energy. We have relativistic kinetic energy from last chapter, although chances are this won't be relativistic. And we just have from physics 1, kinetic energy is 1/2 mv squared. Assume it's not relativistic unless it says otherwise. And so if kinetic energy is 1/2 mv squared, if I multiply both sides by Ke, divide both sides by m, I'll get that v is the square root of 2 Ke over m. And therefore my velocity is going to be the square root of 2 times the Ke I just got, 6.119 times 10 to the negative 20 joules, over the mass of an electron, 911 times 10 negative 31st. I have that memorized. Square root off. And you'll get that it'll come off at a whopping 3.67 times 10 to the 5th meters per second. Not fast enough to be a relativistic speed, but still a pretty big speed. I seriously keep looking and talking to the camera even though it's not working and you can't see me. Habits. Any questions though? If I put the photoelectric effect on final, it'll probably be something involving this type of stuff. You know, find a cutoff, find the kinetic energy, maybe do something with kinetic energy. It'll be related to these if I do a work function one, or a photoelectric effect one. Thing is on the exam, I might not go photoelectric effect. I could also go some of the other stuff from this chapter. And so this next problem is part of that other stuff. And it says, a photon with a very small wavelength, fraction of a nanometer, it scatters from a free electron, which is at rest. For what scattering angle does the recoiling electron have kinetic energy equal to the energy of the scattered photon? So let me get it. For what angle does the recoiling electron have kinetic energy equal to the energy of the scattered photon? Okay. Well, what we have here is an electron scattering off a photon. A photon scattering off an electron. I said that backwards. Basically, this means, and I'm opening something else up as I talk to just display for your benefit. Let's say how to ESIC. There we go. Is that a photon's coming in, hitting an electron, and the photon's going one way, the electron is going the other. This is called Compton scattering, and be used with the equation that the change in wavelength of the scattered photon is the wavelength minus the initial wavelength of the scattered photon. And what that's equal to is Planck's constant over the mass of an electron times c, 1 minus the cosine of the angle. Now, we can talk about the energy of a photon. The energy of a photon, once again, is hf. And I can use the same logic I did on question 1. I'm not going to bother going and doing it again. I can say the energy is then hc over lambda. And so the initial energy is going to be hc over lambda, which I know. I know lambda. Oh, I should really say hc over lambda naught. After the collision, it's going to have an energy of hc over the new lambda, whatever it is. And after the collision, the electron will now have energy. However much energy that is. But we can assume conservation of energy. I know it's a collision, so you'd probably think conservation of momentum first. But the thing is in a problem like this, energy will be conserved. They will have elastic collisions because it's a wave bouncing off a particle, even though light can also be a particle. And so what I'm going to do is I'm going to say energy will be conserved. Energy initial equals energy final. Side note, this is probably harder than I'd put on an exam because it takes some leaps in logic. This being the big one. Thinking to do conservation of energy is a big leap in logic here, so this probably would be on an exam. And what I say is initially, well, let's use the same notation. Yeah. Initially, I have just my photon. Final, I have my photon, but also this electron's now moving. And now has some energy. Now, I also said that let me grab my highlighter, is that the recoiling electron has the same kinetic energy equal to the energy of the scattered photon. That means this and this is the same. And if this and this is the same, that means that's the same as saying that the energy here is 2hc over lambda. Now I'm going to take this new equation I just got and divide both sides by hc. If I divide by both sides by hc, I get 1 over lambda naught equals 2 over lambda. Cross multiplying, I'm going to multiply both sides by lambda, then multiply both sides by lambda naught. I get lambda equals 2 lambda naught. And I want to take this and go back up to my Compton equation and say, okay, if lambda equals 2 lambda naught, I'm just going to take this lambda and plug it in here and say 2 lambda naught minus lambda equals h over MEC, 1 minus the cosine of the angle. But 2 lambda naught minus lambda naught, sorry, I missed that naught. That is lambda naught. So lambda naught equals h over MEC, 1 minus cosine of theta. From this, I'll multiply both sides by MEC. The only line I'm getting rid of right now, when I move this up, I will box the two lines I got rid of in case you want to keep track. I got rid of this line and this line. So multiply both sides by MEC, divide both sides by H. I can then add this to both sides and subtract that from both sides and say the cosine theta equals 1 minus lambda naught MEC over H, which means the cosine of theta equals 1 minus lambda naught 0.0016 times 10 to the negative 9 meters times ME 9.11 times 10 to the negative 31 kilograms times C 3 times 10 to the 8th meters per second over H 6. I didn't give it. Okay, 6.63 times 10 to the negative 34th joule seconds. Oh, I'm off the bottom. I'm sorry. And eventually I'll get the cosine of theta is 0.3401. I'll then do the inverse cosine. And get that the angle is really exactly 70 degrees. I feel like I dropped sig figs here. 0.3401. 70.1 degrees. As I said, this one's a little harder because you had to do this leap in logic with the energies up here. I think traditionally, if I put something like this on the exam, and by traditionally I mean there's only been one exam before, not counting this year. But I think I did Compton Scattering last year. I'd have to check. I'd go a little more straightforward, and you would have to make that leap of logic. Yeah. Any questions on that? So one of the other big things we did this chapter, so no. Huh. One of the other big things we did this chapter was we talked about X-rays. So what minimum accelerating voltage is required to produce an X-ray with a wavelength of 70 picometers? So lambda is 70 picometers, which is 70 times 10 to the negative 12 meters. The equation for an X-ray, it's written right up there. We know lambda min equals HC over EV. I want to multiply both sides by V, divide both sides by lambda. And just kind of plug in. That's kind of the entire problem.
Dr. Lars, quick question.
Yep.
When you have HC on the top, why is it 7 times 10 to the 8th? Is that just like a...
Oh, that was a 3. It's just bad handwriting.
Oh, okay. I just can't even see it anyway. Thank you.
It was a 3 that instead of being pronounced kind of became a little less pronounced to just become nothingness. This is obviously a lot simpler than something I'd put on an exam. Might just be part of an exam problem. Huh, this is number 5. Sorry, I just realized that there's a 5 here. Did it skip a number? 4, 2. Yeah, there's no problem 3. Cool, I have to fix that. Problem 6. Problem 6 says, an electron and a bullet each have velocities of magnitude that, with an accuracy of this. What is the lower limit? Can we determine the position? Okay, this is getting into uncertainty. This is Heisenberg uncertainty principle. Before I do Heisenberg uncertainty principle, I just want to state something. This packet did skip one type of problem. It didn't have anything with de Broglie wavelength. That can show up on the exam. It will show up on the homework. It's just wavelength is h over p or h over mv, whichever one is easier for you to use. I didn't put it in here because it's just like one line, but that could also be a thing. But this is about uncertainty principle, that the uncertainty in position is the uncertainty in momentum times h over 4 pi. I'm not going to bother rewriting it again. Now, we say that this has a velocity of 500 meters per second, and the accuracy of it is 0.01%. To get the uncertainty, I'm just going to take this 500 meters per second and multiply by 0.01%, or 0.0001, converting my percentage to decimal. That means it's 500 meters per second with an uncertainty of 0.05 meters per second. But that's not V, that's sigma V. Now the equation is sigma P, but we know P equals mv. If your mass is not in question, which it usually isn't for such things, I can say sigma P equals m sigma V. And if I go back to my equation that I had boxed, sigma x sigma P is, well, we want the lower limit. If I want the lower limit, I'm going to set these equal instead of the equality, because that's going to be the limit is when they're equal. H over 4 pi. That means sigma x m sigma p equals h over 4 pi. And if I want the uncertainty in position, the uncertainty in position is going to be h over 4 pi m sigma v. Oops. I left that as a p. Because and so it would be 6.63 times 10 to the negative 34th over 4 times pi. Let's do the electron one. 9.11 times 10 to the negative 31 kilograms times 0.05 meters per second. There's something wrong with my answer here. Oh, I did the bullet first. That's why it confused me. And you get 0.00116 meters. I probably need to answer that, but that's still in class. If you wanted to do for a bullet, you would just replace this number with the mass of the bullet, and you'll get instead 5.27 times 10 to the negative 32nd meters. And this is why in classical physics we don't deal with the uncertainty principle. This is so tiny you'll never have to think about it. But this number for an electron, That's 10 to the 7th times bigger than that of an electron. That's going to be important. That's going to be crucial, and we're going to have to deal with it, though. Any questions, though?
Nope.
All right. So I apologize. My camera wasn't working. I will restart my computer for next time. Basically, I signed in 10 minutes before, and when this happens, it takes my computer about 15 minutes to reboot. So I didn't do it. Figure you didn't need to see me today, anyways. So I will wrap up that. Next week, we'll start the last chapter, which really is dangerously close to chemistry. We're going to continue with quantum physics and use quantum physics to describe the atom. And then we're going to get into the quantum mechanical version of the atom. And then once you start talking about atoms, it becomes chemistry. So we're going to hit the bridge to chem. But other than that, have a good weekend, and I'll see you all Monday.
Have a good
Have
one.
a good weekend.